We looked at the common source and the common gate noises. So today we'll look at the source follower. We'll look at the source follower, the cascode and the differential amplifier today. What is the output impedance of this? We did this right in the first couple of classes. What is the output impedance? Louder please. RD1 parallel RD2, is it? Okay, please check again. What is it? Exactly. 1 by GM1 in parallel with 1 by GMBS1 in parallel with RDS1 in parallel with RDS2. Okay. In other words, G out is GM1. Okay. So what is the output noise? Gamma 1 GM1 plus 4K2 gamma 2 GM2. That is the current noise coming from each one of these times 1 over G out squared. Okay. So now you can write, the gain of this also, right? It's just GM1 over G out, right? Okay, so this is the input referred noise of the source follower. And if you see, it actually looks very similar to what you derive for the common source with the PMOS current source, right? It's not very similar, it's exactly the same. Okay. The gain is less than 1, right? And the input referred noise is the same. So you typically don't prefer this in low noise amplifiers. Okay, there may be special cases where you might need it, but in normal low noise amplifiers you prefer to get gain along with noise. Okay. Okay, yes. Actually no particular reason. We are just assuming that if you can write the same thing for the flicker noise, right? We are just not, I'm just writing it because thermal noise is easier to calculate. You can write the flicker noise and calculate it out. It all depends on the bandwidth under consideration. If the bandwidth is very wide, you may be interested only in the thermal noise. That's all. That's the only reason. Okay. In the general case, you have to consider flicker noise and include it in all your calculations. But it won't be very different, right? Basic idea is you take the current noise, right, multiplied by the output impedance divided by the overall gain. That is the general procedure. So in any circuit, if you have noises, if you want to find out let's say the overall output referred noise, you take it multiplied by mod of h of j omega the whole squared from that point to the output, and then divided by the overall gain of the block to get the input referred noise. Okay. Okay, so now let's look at the cascode. So first what we'll do is let's just take into account this one and this one because it's easy. The current noise flows through to the output, right? We know that. RD directly flows to the output. So let's just write the expression for M1 and RD first. Then we'll start considering M2. What is this? We already know this, right? This is the noise current due to RD. This is a noise current due to M1 multiplied by RD squared. That is the output voltage noise. Right now we'll ignore again 1 over F noise. The voltage gain of this is also minus GM1 RD. What is this? It's just okay. One more. Okay. Now what about M2? So let's try to see what happens to the noise of M2. So let's draw the circuit with the current source, the noise current source. Okay. So if you look at this noise current source, what happens? There are actually two portions to this noise. So one portion of the noise flows like this. The other portion of the noise just keeps flowing back through M2. Correct? So this noise basically splits at both places into two portions. Is that clear to everyone? Okay. What is the noise we are interested in? We are interested in the noise obviously which flows through RD because that is what creates the output. Right? The output impedance here is very large. That's in parallel with RD. So you want to find out the noise, right, which flows through RD. What is that portion? How do you think the noise will split? How do you find that out? Sorry? Sorry, not. Correct. And so, okay, output impedance parallel with RD, correct. And so what do you think will happen in this case, the case of the cascode? What can you say about the relative ratios of the two currents? Well, you can look at it two ways. So suppose you look at the current splitting in here. What is output impedance here? Looking down? RDS1. What is the output impedance looking out? Input impedance looking up? 1 by GM. So what do you think is going to happen? How much current do you think is going to flow here? How much current do you think is going to flow here? Most of the current will tend to flow back through M2. Right? So in other words, the amount of current which is creating noise at the output is going to be very low. Okay, so because this is the current we are interested in. Because this current just keeps circulating, it doesn't even go to the output. Okay? So let's write this out specially. So flows through and if I call this Z in 1 and I call this Z in 2, so it depends on the ratio of Z in 1 to Z in 2. Okay? So in other words, M2 actually doesn't produce a lot of noise. That's what you find out. So in other words, if you have a cascode structure, the cascode transistor does not contribute a lot of noise. at the output. Okay, and that of course depends on the ratio of the input impedance and the output impedance of the transistor. Okay, is there another way to look at it? Suppose, so remember, for any transistor, this output current noise, for each transistor you can also refer it back to the input and look at it as an input referred voltage. Right, you just divide it over the GM. So you take the transistor itself as a 2-port, look at the input referred noise. What is that going to be? It's going to be this current divided by the transconductance. So if you have 4 kT gamma GM here, you're going to have 4 kT gamma over GM at the gate. Correct? What is this? Okay. What is the gain from here to the output? What is the gain from here to the output? GM into? Well, for this it is GM into RD for a normal common source. What is it for this? It's not GM into RD. Okay, so what you want to find out is the effective transconductance of this combination. Correct? That's the easiest way to do it. Right? And then that current flows through the output through RD, and you can find out, multiply that by RD and find out the overall gain. What is the effective transconductance of this portion? From this point to the output. What is it? Well, you're close, but not correct, but you're close. What is it? Okay, so first of all, let me, okay, what is it? With the, correct, okay, so the gain is, oops, what is this? This is basically GM2 RD over, correct? What is the output impedance looking in here? It's RDS1. Remember, we calculated the gain of a source degenerated common emitter. What is that? The effective transconductance is GM over 1 plus GMRS if you have an RS at the source. So the effective gain of this is GM2 RD over 1 plus GM2 RDS1. RDS1 is very large compared to, right, the other resistances in the circuit. So what is the effective transconductance? Extremely small. Okay? So the gain is extremely small. So in other words, this transistor does not produce a lot of noise at the output. That is another way of looking at it. Okay? Okay, so remember that because it's a pretty important result, right? That the Cascode does not introduce a lot of noise. You have actually put in a extra transistor there. It increases the gain of the circuit. You know that if you use it properly, but it tends to not add a lot of noise. But that you have to be careful because if the impedance at the drain changes, that may change. Okay, just remember that. In this case, we have used an RD, right? Which we are assuming is much smaller than the other resistances in the circuit. If you put in a current source there, the case may be different, right? Obviously, it will turn out to be different. Okay? Okay, now let's look at the noise of a differential pair. How will you write this? Now again you have to consider 2 port, but now the earlier in all our circuits, one of the, if you look at the input port, one of the terminals was grounded. Now it's a differential input port. That's all it is. That's the difference. Apart from that, you can draw exactly the same 2 port equivalent circuit. Okay. So if you look at the transistor noise, it's ID1 squared and ID2 squared. Since they're coming from 2 totally different transistors, those 2 noises are completely uncorrelated. Okay. In other words, what this means is, when you do your normal diff pair analysis, what do? You separate it into the half circuit and then calculate out the, the gain and so on, the transconductance gain and so on. In this case, because these 2 are completely uncorrelated, in that case it was completely correlated and negative. Right? That's why you could break it up into the half circuit. Here, because it's uncorrelated, you can't break it up into a half circuit. You have to do a full analysis. You have to start by looking at each noise separately and then find out the input referred noise for each. Okay? So let's try to simplify the circuit. Let's say now we are trying to find out the noise from M1. Okay. Now if you want to simplify the circuit, I want to write let's say I want to find out the noise going to this output, right? I want to replace the rest of the circuit by some impedance. What would that impedance be? This is a current source. Assume for now there's infinite output impedance. Okay. Now what else, if I want to redraw the rest of the circuit as an equivalent circuit, what can I redraw it as? Okay. 1 by GM2 plus GMBS2, right? Okay. Is that clear? What is Zn here? So this is similar to the cascode where the current is splitting 2 ways. One going up back into the transistor, one going in here. Okay. So what happens? 1 over GM1 plus GMBS1 is the same as 1 over GM2 plus GMBS2. So half the current will flow here, half the current flows through this. Correct? So what voltage does it produce there? Into RD2 squared, RD1 squared. Correct? Okay. What happened to this current flowing out here? So this half current flows out like this and then flows through this. Where does that flow? flows through RD2, correct? So it's going to create a voltage here, right? What is that voltage? RD1 square by 2 times RD2, okay? And the direction is opposite. So if you take the differential one, they'll add up. It's correlated also. It's the same current, right? Okay. So what that means is you get ID2 times ID1 squared over 2 times RD1 on this side plus ID1 squared over 2 times RD2. If RD1 equals RD2, then it is just ID1 squared times RD. Similarly, M2 will produce ID2 squared times RD. Okay. Times RD squared. Sorry, I said RD, but it's actually RD squared. Right? Is that clear to everyone? Okay. What is the total one? Now you can add the resistor noise also. Resistor noise, you already know how to do that, right? Actually, let's just call it 2 into 4 kT RD. Okay? Plus ID1 is the same as ID2, which is 4 kT gamma GM1 and 2. Right? This is a differential pair. All the transistors are identical. Both the transistors are identical. What is this? Okay. So now you can find out the input referred noise. What is the gain? It's GM squared RD squared. Simple diff pair. Okay. So it's just 8 kT gamma over GM1 plus 1 over GM1 squared RD. Does this look familiar? It's basically twice the noise of a common source, right? Okay? Yes. But you're not supposed to consider the half circuit, right? Because the currents are not correlated, right? Right? I mean, had you considered, I mean, you can consider it and get the right answer with the wrong, method, right? That's not considered correct. So if you just look at the voltages, the noise voltage is root 2 times the noise voltage in a common source, right? The effective input referred noise voltage, not the noise voltage squared. Okay? So have we considered all the noise sources? M1, M2, RD1, RD2. What about IT? Right? It's a current source, but you would obviously implement it using transistors. So IT is going to have its own noise. How do you think IT noise is going to behave? Yes. So let's assume you have a noise source in parallel with this, right? You can call it IT squared, IN squared or whatever. What is going to happen to that noise? Why? All the current flows through? Okay. So the current will basically split equally on both sides, the current noise. So at the output, it will appear as a common mode noise. If your circuit is completely symmetric, the differential noise goes to 0. Right? Okay. So it appears as common mode noise at the output. If everything is balanced. If everything is balanced in the sense, Vn is 0. Appears as common mode noise. What happens when Vn is not 0? If your input voltage is not 0, there is actually a real imbalance, because now one side has more, at any instantaneous point, one side has more current than the other side. You have a delta Vn at the input, correct? So let's consider what happens when you apply a delta Vn at the input of the differential pair. So we'll calculate the difference in the currents, because that's what we are interested in. What is that? It's just Gm times delta Vn. Correct? It's a small signal. We are assuming it's a small perturbation. Now we can write Gm So if you have the noise current, that noise current is going to cause a small imbalance. Okay? So if you have noise current flowing through 1, it's going to be IT plus IN over 2. And now what we can do is, we can pull out this IN term, it's a small compared to IT, you can pull it out of the square root. You know how to do that, right? You've done it multiple times. What does this give you? Gives you something like this. Okay? What is this? This is just your Gm naught, delta Vn. Oh, sorry. Yeah, that's right. Okay? It's IT by 2. That's a Gm of, yeah. Okay. So what you do is, IT plus IN whole divided by 2. Oh yeah. Good. Yeah, that's right. Wait. And then you'll get the other 2 when you pull it out of the square root. Right? Because so that is inside the square root, you get 1 plus IN over IT, and then you pull it out, you get IN over 2 IT. Okay? So what is this? This is actually a differential noise at the output, because it's delta ID1 minus delta ID2 multiplied by RD, right? You'll get a differential noise at the output. But you also note that it's actually multiplied by delta Vn for small perturbations. Typically, if your Vn is quite small, right? If you're considering small signal, this is not a very it's not a very prominent effect. Okay? Normally, the current source noise is suppressed to a large extent. Okay? Suppose you have a cascade of two amplifiers, right? If you look at the overall input referred noise, which is going to contribute more? Why? So, if you look at, you can replace the input referred noise of each one of these blocks at the input. And if you want the overall input referred noise, this input referred noise gets divided down by the gain of the first block. So, if you have a cascade of stages, the noise of the second one becomes less prominent. Okay, so that's why if you look at many systems, the noise of the first stage, if you have multiple amplifiers, you are much more worried about the noise of the first stage rather than noise of the succeeding stages. Suppose you have a network of resistors, capacitors, inductors and transistors. Okay? The certain participation PD. Let's say this is R, L, C and width W. And it has some noise path spectral density Sn at the output. In volts square per hertz. Suppose you want to reduce the noise of the block. You can scale each one of these appropriately such that the overall noise gets better. How would you do that? Make the resistors 1 over n, inductors L over n, capacitors n times C and width n times W. Remember, this is very intuitive because remember that your resistor noise contributes to your input referred noise. So if you want to reduce the resistor noise, make it smaller, right? Reduce the transistor noise, you want to increase the GM, right? The participation will become n times the original participation. Okay? And you'll get the new path spectral density will be 1 over n times the old one. Why don't you try this out for some circuits? So take some networks and try it out, see what happens. Okay? Okay, so we are going to stop with noise at this point. Okay, do you have any questions on noise? We're going to stop with noise now because this is basically an introduction. We've already covered like more than a week of noise. We're going to move on and look at other things. We're going to look at mismatch next. Okay, then we'll come back to noise when we start looking at op-amp structures. Okay, we'll start looking at the noise performance of different kinds of op-amps. So that's when we'll come back, maybe in a few weeks. Probably much later in the course. Okay. So what do you understand by mismatch? Has anybody heard this term, mismatch? Of course, with respect to circuits, not, don't tell me something else, right? With respect to circuits. No, okay. So what this means is, you are trying to, let's say if you have a circuit, you want two particular components to be identical or you want them to be exact multiples of each other. One of these two, right? There are many cases. We looked at the differential pair, you want RD1 to be same as RD2, you want M1 to be same as M2. All our analysis is based on that, right? Similarly, if you have you have an op amp gain stage like this, let's say if you want an exact gain of 2, right? If you want an exact gain of some n or something, so R2 should be n times R1. Correct? So there are cases where you want them to be identical. So let's say if the gain changes from the actual value, that could be a problem for your circuit. So that is called mismatch. So if the two are not identical, that's called mismatch. So if you see, it actually has mismatch in circuits has two components. One is systematic, the other is random. Okay? Systematic mismatch you can definitely do something about. Okay? Random mismatch, you can do some things, but there's not a lot you can do about it because it's beyond your control. Okay? It may be limited by the process, it may be limited by some other, some other process which is not under your control. Okay? So what we are going to do is over the next few classes, the next 2-3 classes, we're going to look at the sources of systematic mismatch and random mismatch. Okay? Systematic mismatch is pretty straightforward. There are, very clear ways how to tackle it. Okay? Let's look at some examples of systematic mismatch. So let us say you have a capacitance, you have two capacitors, you want the capacitance ratio C2 to C1 to be 2 to 1. Okay? So you could have C1, C2 is larger, so each one has a certain length to it. Maybe this one has double the length. So the overall area is, so it looks like on the face of it, it looks like if you make this 2L and W, L and W, on the face of it, it looks like they should be twice the other. Okay? In reality, so ideally, let's say this is the side view of the capacitor. You want these, the lines to directly pass through, field lines to directly be vertical, go from one cap to the other, okay, for a parallel plate. But in reality, what you have is, you have these fringing field lines on the edges. Okay? Why? Because that is where actually you have a sudden change in boundary conditions for your capacitor, right? Everywhere else inside, you have capacitance, you have metal plates on all sides. Electric field lines have only one way to go, right? Out here suddenly you have, sudden mismatch, right? Sudden change in conditions. So what happens? Eventually the field lines will end up at the other plate, but you have fringes. Same thing here. You're going to have fringes on this capacitor also. Okay? Will the fringing capacitance be the same on both cases? Probably not. Is it going to scale with the area? Probably not. Okay? And it doesn't. It turns out it doesn't. Okay? If you express the overall capacitance in terms of the actual parallel plate capacitance and the fringing capacitance, so you have some capacitance per unit area, let's call that C area, times the L times W, that is your parallel plate capacitance. This is the ideal capacitance. But then, you also have some fringe capacitance, which depends on the perimeter. Okay, because that's where it's at the edges where you have the fringe capacitance. Okay? So now, if you try to create identical structures by just doubling the area, definitely the fringe capacitance is not going to scale the same way. So this is a source of systematic mismatch. Okay? So one thing you can do is to lay out the capacitance in terms of unit cells. So instead of using two of these, if I do this, right? Instead of just using double the length, I lay it out as 1 unit, I lay the source as 2 units. Then definitely the capacitance will be a better multiple, closer to 2 than what you got in the first case. Okay? But now you are still going to have mismatches in the environment. So the basic idea is fringing capacitance is one way. But there are other things. For example, you could have changes in the environment on other sides. Okay? Let's consider this side. So this unit cell has nothing on either side. These two unit cells on one side, they actually have something. So that is going to change your capacitance slightly. So now what you would do is, add dummies. The same unit cells, replicated. Except you are just going to ground them. You don't use them at all. But you use them to match the capacitors. Okay? Now it will get even closer to the actual ratio you want. So now the environment is identical for all of these. Okay? Now this is the case of 2 to 1. Now the nice thing about laying out this unit cell, you can achieve lots of fractional ratios. If you want 4 to 3, you have 3 units on one side, 4 units on the other. You can get random large numbers. Like if you want 97 to 33 or something, you can get, you can just lay it out in unit cells, find out the lowest common multiple, right, of the two, and lay it out that way. Okay? You can achieve all kinds of random ratios. Okay, that's a simple example of a capacitance. Suppose you take a resistor. Again, you have systematic mismatches. So let's say suppose you want 2 to 1. Okay? So let's say this is R1. Okay? So let's say this is your resistor, you have the contacts on either side. So now what's going to happen? The actual resistance, you have the resistance of the contact itself. Okay? So you're going to have this, the overall resistance is going to be resistance of the contacts plus the actual intrinsic resistance. So the actual resistance is intrinsic resistance plus 2 times R contact. And if you try to lay out, if you want to try to lay out R2 as twice, then that will also have the same. Any value of resistor you add will always have 2 R contact. Intrinsic resistance will change. So there will always be some systematic mismatch component. So how do you get rid of that? Again, same thing, unit cells. Okay? Oops, sorry. This is R2. Okay? So what is the basic idea? So if you take a resistor, for example, there are also other systematic mismatch components. And in general, for transistors, anything. You could have, for example, you have your process which is actually depositing your resistor. If it's a, let's say, if a diffusion resistor or something like that, you could have a temperature gradient, right? This resistor could be in one spot. This resistor could be at some distance away. There could be a temperature gradient. So the deposition rate, all those things, the process parameters will change. So the actual resistivity could change in one direction, right? You could have a pressure change, right? When you're creating your mask set, you could have a gradient on that in the lithography. So there are lots of systematic errors you can introduce while creating these resistors. Or it could be transistors, right? In the case of the transistor, it could be this deposition rates could lead to a change in VT, it could lead to a change in doping concentration, mobility, right? Lot of things. And there are certain set ways to deal with these kind of effects. One way is what we just discussed. Try to create the same environment, and if you look at process gradients, we'll consider in a later class, we'll consider ways to lay out the transistors or lay out the resistors or capacitors in such a way that from any direction if you see the systematic mismatch, is minimum. Okay. So what is the general idea? Of course, same environment. That is a fundamental thing. Next thing, same orientation. Because now if there is going to be a directional gradient, you want them to be oriented. You can't make one resistor like this, other resistor like this. Okay? Or one transistor like this, the other transistor sideways. Drain source. Okay? So these two things are very important. And of course, what we discussed first, identical, try to split it up into units. The smallest unit, which is a common factor. Or it could be the largest unit, which is the common factor, right? Now let's take the example of let's take the example of a current mirror, right? So let us say you're going to do 1:2 for the current mirror. Okay. How would you lay this out? So I'm going to move to the next page, but just remember M1 is 1 unit, M2 is 2 units. And let us say I'm going to start naming this thing, coloring nodes here. This node is blue. So let's say this node is red. And this is whatever color this is. Okay. I'm colorblind, so I can't tell, okay, what these colors are. But, okay. So let's go over and so let us say we're going to lay these out with 2 fingers. We have looked at this layout before, right? Basic layout we have looked at for the transistor. So let us say this is M1. You've laid out 2 fingers for M1. Okay. How many fingers do you need for M2? 4 fingers, right? It's 2 twice. Okay. You're taking care of these, yes. These are the gates. Remember, we looked at the gate drain source connections we looked at the layout view of a MOSFET in the first or second class. Okay. So these are the gates. These are the drain source connections. Right. This is basically the top view of the transistor. Remember this? You guys, okay. So this is the width of the transistor. This is the length of the transistor. So the width, this is the gate. So the thickness of this in the top view is the length of the transistor. We looked at this in the first class. Does anybody remember that? Okay, at least some of you do. For M2 we are having 4 fingers. This is just an example. You could have 1 and 2. So obviously M2 we are trying to get a mirror ratio of 1:2, right? So the actual number of fingers for M2 should be double that of M1. That's all. Here I just took an example of 2. Oh, I see. Okay. So you can lay out the transistor. So it's effectively a way of folding the transistor over. Okay. If you just use okay, good thing you brought that out. So let's say you want a transistor with W over L. This is W over L. Okay. You could also draw the transistor like this. It is basically like having two W over 2L transistors in parallel, right? This is this. This is effectively the same as having two transistors in parallel, each with W over 2 and same length L. So the overall width is going to be W over L, right? Okay, actually, you know what, let's stop here, it's already 8:55.